Hey guys, welcome back to another video. Today we're going to be doing some Python optimizations. Okay, so let's just begin. So firstly, in Python there's this function called sum. It just takes the list of elements and it sums it. So here we import timeit, which is going to be our benchmark library of choice, and then we have this function benchmark that just takes in the function, runs it 100,000 times, and then, averages the time, returns it in seconds, right? So we'll start here with our slow function. It takes 17 seconds to run, and basically it's just summing up a list of elements. So the reason why this is so slow is because we're allocating memory for that list every time we call that function. It's a pretty big list, and we're just summing it. So we don't really need we don't need to generate a list like that every time. So we could do a little bit better by using a range. So instead of allocating all this memory, we're just allocating a range pretty much. And then we can get even faster if we use NumPy. So 0.5 seconds is crazy fast compared to the other results we had. This is because it's using C in the back end instead of, interpreting bytecode or Python bytecode or whatever, right? So use NumPy if you have large arrays that you want to do like operations to. It just makes it a lot faster, right? And then we can actually get faster than the NumPy version. I don't recommend JIT compiling everything, but sometimes you just feel like it, I guess. And you just wanna JIT compile all your functions. You can if you want. You don't have to. I think NumPy will kind of like most libraries will kind of be efficient enough where you don't have to do this yourself. But basically here we have the same thing as like here that took 13 seconds, and we're doing it in 0.1 seconds. So just think about that. And why does that work? It's because we're not interpreting bytecode, we're interpreting machine code instead. We're not interpreting machine code, we're generating machine code on the fly and just running it. So it's near native performance, basically. Alright, so that was that. Let's do the next one. String optimizations. Let's see. We have words. It's just a list of 3 words times 1,000, so 3,000 words. And basically, we're just combining all the words together and joining it with a string or joining it with a space, and then returning that sentence, right? So sentence, it's nothing at first. Then we go through the for loop and just continuously add in every word plus a space. So it takes 13 seconds, which is pretty slow compared to our faster solution where we just use Python's built-in function join, because Python they basically just optimize all their functions or their standard library functions. So usually you can get by with just using Python's standard library functions for like most things, because they will be fast enough. You don't have to implement this yourself. So. And plus, in Python, the for loops are pretty slow. So, yeah, I mean, over time it has gotten better, but usually you kind of want to avoid using for loops. So, for example, use filter or map or whatever. Use the functional functions, right? They're usually a little bit faster than the for loops, just because Python's bad with for loops. All right, so. Yeah, basically you want to check if there's an element in a list, and Python has this built-in keyword called in, and so you take whatever, or you just pretty much ask the list if it has this element. So here it takes 64 seconds, which is crazy, because we're basically going through each element in that list and checking, is this that element I'm looking for, and in this case it's really bad because for the majority of the list, no, this is not that element. So this is basically O of n, right? Because you're going through each element of the list, but we could do a lot better by converting this list into a set, and basically it's just instant, because whatever you're asking for, it'll just put it into a hash function, and then the hash function will lead to a certain memory, just a certain location in memory or whatever, how a hash table works, right? So you just instantly kind of go to the place you want to go if it exists, and you'll instantly kind of just not go anywhere if it doesn't exist, right? So Yeah, so that's like 0.02 seconds. That's pretty good compared to this. That's like, I don't know what percent increase that is, but it's a lot. Also, I do want to mention we are going through a sorted list, so you could benefit from using a binary sort or search. My bad, and that'd be passable. I'd be fine with that. If you're like, because if you're only gonna run it once, just do it. Just do a little binary search, just real quick. Like you don't have to you don't have to convert the whole list into a set if you don't want to. You can just binary search. It'll be like pretty fast. I don't know I don't know how fast, but definitely a lot faster than that. All right, let's go on to the next one. Number 4, we have list comprehension, and as you can see here, we're just building up a list of squared numbers, right? And we're building it kind of manually. Like right here we have list comprehension. Right here we just have like kind of the same thing, just different format. So this took 35 seconds, and then we get an amazingly like large increase right here, or in performance, 34 seconds, right? It's not actually that much faster, so I don't know if you consider this an optimization, but it is a lot cleaner, so I do recommend doing this over that. People probably appreciate this more than that, because like think about it. This takes you gotta read line by line, right? And that takes time. You're wasting precious computation, but of the brain. So yeah, just do this one-liner. You just look at it and you instantly understand what it is, right? Pretty cool. So it is an optimization, trick, but not in the sense of computation, more of like, in your brain. All right, so you could also JIT compile. I don't think I JIT compile everything. I think I just did that a few times. I don't think this should be the last time you see me JIT compile throughout these. So basically, we did save 15 seconds from the original, which that's a pretty solid improvement. I like when I initially did this, I thought it was gonna improve a lot more, but it didn't. So maybe I'll look into that. I'm not sure. Okay, we're gonna go on to the next one, generators. And if you look here, these functions are identical, except you can see this has parentheses right here, and this has square braces. So this is creating and allocating that list like just every time you call this function. So it takes 14 seconds, which is like slow compared to this, which takes 0.02 seconds, because this isn't actually doing anything at all. Like you're not allocating any memory really, and that's why it's instant. So if you ever do any functional programming, there's something called like lazy evaluation, and that's what this would be. So creating generators would be good for like creating, like, say you want to generate prime numbers or something. You don't want to just like automatically calculate all the prime numbers at once. You just want to calculate them as you need them, or something like that. Or say you have a tokenizer for a programming language. You don't want your tokenizer to return like all the tokens at once. You don't want it to like just go through all the text and just generate tokens and store all those tokens. You'll have like your tokenizer will probably generate a couple tokens, and then so your parser can just read a couple tokens at a time, so you're not wasting all that memory. You get what I mean? I don't know. Okay, so next one. Okay, we got default dictionaries. Which basically, okay, so we have a list of characters, or it's just a string, hello times 1,000, so like 1,000 hellos, and then we just basically count every occurrence or character occurrence, and then store it into this dictionary. And this isn't that bad, actually. Like, you can't really improve on this too much, but if you use a default dictionary, like you see here, like, because here we have to like check, okay, so if character is in counts, we increment it, else we just set it to 1. Here you don't have to do that. You don't have to do that branch prediction, or your CPU doesn't have to do that branch prediction, because you're not branching here. You're just automatically just incrementing 0 to 1, right? Because everything is just automatically 1. or I mean 0 when you get it, right? So that's a pretty good optimization. You save 5 seconds. Pretty good. Well, just in this benchmark, I mean. Alright, so number 7, we have a DQ, or a deck, or I don't know how to pronounce it, but yeah, we have it. So for our slow function, we have a queue, it's just a normal list, and then we insert into the front, and basically when you do that to a normal list, it's just like you have to move every element in that list to the right, and then eventually you'll have to also reallocate a new list and then place all the old elements into that new list once you hit that certain capacity of the, it's basically there's a little space in the list, a little buffer, I guess you can call it, of where you can put the new elements, and then eventually after you keep adding elements, that buffer just becomes full, and then it has to reallocate the more, and it does this, and then there's algorithms that do this efficiently, right? So I kind of just went on a tangent a little bit there, but basically this is slow because you have to, first off, you have to shift every element to the right, and then also sometimes you have to reallocate to a new list, which is, computationally expensive. So that took 136 seconds, whereas this one took 10 seconds. And why this takes 10 seconds is because a DQ is kind of like a linked list, so it's pretty good at insertions from the front and the back, and also deleting, because you're just changing a pointer. So you allocate your memory and then you just point to it, and it's kind of, yeah, so basically just like a linked list. And also it does look better, it's more readable because you have this append left instead of this, disaster. Who's going to be able to look at this code and just understand it? I mean, you can kind of take a guess, but yeah, this is append left. It's a lot more readable. So I do recommend, if you have to do some sort of if you have to do some sort of operations like this, it's O of 1, so that's pretty good. Okay, so to the next one. Okay, so this one we have least recently used cache, or LRU, and basically right here we have just a normal Fibonacci function, generates some computation, and when you have a function like this that always maps the inputs to the outputs, it's so given a certain input, you always get that certain output. That's how you know when you can kind of benefit from caching. So here, since the result's always the same given the input, you can cache it, and see how this took 50 seconds? This takes 0.009 seconds, because this computation only ran once, because it's cached, right? So it does cost. Okay, so there is a trade-off between memory, but I'd say it's probably worth it. So if you have some sort of heavy computation like this, yeah, use an LRU cache. Alright, so I think this is going to be it for the video. I did have more Python snippets, in a different directory, but I think I'll make a part 2 of this video. So yeah, let me just do, where did I go? Okay, so thank you guys for watching, and I'll see you guys in the next video.